think Zoom knows how fucking annoying it is. Like, obviously, I don't want to click that. Make it go away.
It is a good eye.
It might be harder since they laid off 50% of their workforce.
I was saying, it's 500 people.
Well, this is the problem with all startups.
The guy who was working on that exact thing is fired.
Yeah, right. Okay, folks. All right. So I have your homework. I'll give it to you at the end of class, unless you have 120, in which case we'll trade. Okay. Anyone have any problems? First homework. If you don't see the other homework, let me know, right? Because then you can't work on it earlier, get to the help sessions and actually get help. The first checkup is here, week 5. So we won't have class on President's Day, and I'm giving a talk in Berkeley on Tuesday. So that means that you will make an appointment on Wednesday, Thursday, or Friday to talk to me about your progress in this course. Defend it. You can get an A+, but you have to defend it. It's your argument, and we'll talk about how that happens at the end of class on Wednesday. On next one. Okay. Just send me an email.
Okay.
Or Slack or whatever. Okay. And then I hope you've been using progress reports. I give comments and sometimes just like smiley faces. And so some people like that. Some people are like, that's really boring. I forgot to include an image here, so I'll do that later. But we are going to jump right. And how do I? This is like off the bottom of the screen now, and I can't pull it back up. Slideshow. Play from start. Okay. So we were talking about oh great, it's all still up here. We were talking about the kinematics of how fluid parcels deform, how they rotate, and how they become stressed by differential fluid flow, right? So essentially you can keep going back to this picture. This is okay. So you have this differential fluid flow, and that's going to change the parcel. And the way that it changes the parcel speaks to the strains, the stresses, and the rotations that might be in the fluid itself. Okay. So we had this idea, and everyone correctly got the next image. Remember? Probably. You got it wrong. Okay. Everyone but Isabel and Rolando got it. Right? So the points here, okay, they're going to become tilted. This one's going to go farther out. This one's going to go farther out. Now it's really important to remember that in a fluid, this deformation is non-reversible, right? Until you rotate fluid back in the other direction. Right, so you will not, once it's broken off like this, tilted over, that's just the new shape of the fluid parcel. So anything you want to do with it afterwards is subject to that new shape. But coordinate systems don't care about how you originally oriented. So if you orient yourself 45 degrees, then you see that there is just a strain. Okay, it's a strain along these two principal axes. So things that look like stresses can be interpreted as strains. I'm going to keep saying this over because it's not going to make a lot of sense. But we are going somewhere, I promise. Okay. Okay, what's this doing? So I have a particle. Starts up here on the left. This is like a large parcel from Amazon. Maybe it has your favorite poster in it. So I want you to write down just for yourself between stresses, strains, and rotations. There's 2 dimensions here. There's X on the bottom and there's Y on the top. What happens to the parcel as it moves along the streamline? You can write it in terms of the tensors that we have. And thankfully they're all still up. Okay, raise your hand when you're done. Anyone completely lost?
I just don't know if there's a strange business.
Okay, well, there's strain right there, and there's rotation right there.
I know the teacher.
Okay. So is this being strained or rotated or a combination of both? No, you don't tell me. You write that down. What do you mean? Recall that when we move an object from here to here, translation, rotation, strains, and stresses, they can all happen. They're all commutable, right? They can happen one after the other. The orientation doesn't matter. I'm just asking what physically is happening there. Does question make sense?
Yeah, no, I'm just trying.
Okay. Okay, so what do we have? Raise your hand.
I think, so it starts off really, long, and stuff like that, so I believe as it goes across the X direction, it's getting compressed.
Okay.
It gets compressed, and then obviously it then gets distorted back into its original shape, the farther it goes towards the right, towards positive X.
Okay.
Um,
Okay, so that's an interpretation. Are there any other interpretations? Yeah.
Kind of the same thing as them, except I kind of thought that maybe it rotated at that point.
Okay, so you think there's a rotation from here to here? Anyone else? Yeah.
Being compressed in the wide direction, so like it's also being stretched.
Okay. Okay, so you're saying it's stretching because of those arrows that look like it's stretching? Yeah. All right, any other interpretations? Okay, raise your hand here if you think there's rotation. Raise your hand if you don't think there's rotation. Raise your hand if you are not willing to vote. Okay, so most people actually don't think there's rotation. And there isn't rotation. So look at the fluid parcel. Yes, it starts off as this long poster, and then it becomes a square, and then it gets compressed. And even though the shape is similar, it did not rotate to get to that. If instead it maintained this shape the whole time and went like that, great, that would be a rotation. But what would that fluid flow look like? The velocity parcels would have to do this because they'd have to bring these parcels down here and these parcels down here in solid rotation, right? Is that clear? So in fact, I'm a genius because it just sets me up for solid rotation. I didn't plan that, but it happens to be really nice. Okay, so here we have two different examples of vortices. These are idealized. This doesn't really happen. There's no like point in the center. And so you can have, imagine a fluid parcel, A, B, C, D. And here it's not moving very quickly, and here it's moving quite quickly. What is the velocity distribution here? We can read it off.
oh. Omega naught times R.
Right, so increases with R. So how would I interpret the left-hand side of this image?
That it gets faster the further away it goes from the center.
Good. Good. So it gets faster the further it goes away. And what does omega usually mean?
Angular velocity,
So is this moving? How is this fluid moving?
counterclockwise.
Counterclockwise and as a steady what? Okay. Yeah. Kind of. It's not changing its fluid velocity.
Because of the form.
It's non-deforming. It's only rotating. So if you notice here, this parcel stays that parcel because this section here moves farther than this one, but it does so in the same amount of time. So the angles between our parcel edges stay the same. Does that make sense? This is solid body rotation. The whole body, not solid, of course, but the whole thing is moving together like a wheel. And of course, this is impossible because no object goes out to infinity. We like to approximate things like class, right? Yeah. What's the one on the right? Yeah.
What is speed exceed? That is a variable?
The constant. Whatever is necessary. Maybe it's a length. Yeah, sure.
It's kind of like the opposite of what we're seeing, so it's looking at like a sort of looks like it's velocity.
Okay, right. So the radial velocity or the rotational velocity is here, 1/r, right? So as we get towards the center, that rotational velocity goes to infinity. Very good. And as it goes away, velocity goes down. Right? So this is much more like a drain that you might see at your house. Now, of course, it doesn't go off to infinity, otherwise you'd have a real problem, right? But what happens to a parcel here? So the interior edge now is spinning faster or slower than the exterior? Faster. So this moves to the right, and this is trying to keep up. But what will happen in the next time step? More elongated, right? Until until it's basically wrapped around in a spiral. Right?
So it's rotation and spring?
Okay, very good question. So is there rotation here? Why is there not rotation here? Just feels like there's not, because the left one didn't have any strain.
Oh, so is there no rotation because the parcel fundamentally deformed from its original shape? Or-
Well, we can always deform the parcel, right? That would be the strain part. Right? But let's look at another way to look at this. So I have written some stuff up here. I know you're gonna hate this. Okay, but we're gonna do it. No, don't do it, Mateo. What's that thing again? Curl of. The curl of the speed is the vorticity. Yeah. So the vorticity is defined as the curl of the speed. Okay, is there radial speed here?
Yes.
Angular.
There's only angular speed. Okay, so there's only angular speed. So please tell me, what is the vorticity for the one on the left? You're gonna write it down, write out the definition of vorticity. Write it out, and then tell me what that equals. When you're ready, just raise it. I'll come around. Oh, maybe I should have written this too. Hold on.
Yeah,
You have the vorticity in polar directions? Or the, sorry, the curl and polar?
That would be nice.
Okay, hold on, let me write that down.
That would be.
Okay, here is the problem. This is the definition of the curl. Yeah. Just in the direction of Z. Sorry, let me do it this way. You like it this way, right?
It can be east of Z as long as it's about a half nine, no.
God forbid I use a different symbol in an algebra class.
We don't like that thing.
Wait, so is that you on the picture?
Yeah.
Is the U U naught equals omega naught R, is that the same U up there?
Okay, so this one here. Left. U naught or U omega. This is not, that's not a naught, that's an theta.
Oh, okay.
Omega naught R. And then on the right. U theta C over. Okay, who can do the left one? Two omega naught C hat. The left one. Yeah.
The omega naught over R. In the Z hat direction.
All right. Yeah. That's what you said, right? So you both agree?
I also got omega naught.
Omega naught or two omega naught?
We have two mega naught.
Two omega? Is everyone getting the same thing? Okay. Okay. Oh, does that make sense? Does it make sense? Yeah, Z comes out of the page. The vorticity comes out of the page.
Yeah.
It's tangent to the direction of the velocity. Does it make sense though?
Yeah.
What's the left one doing? Only rotating, not deforming. Oh shit, okay, that's what vorticity meant. How much rotation we got in this bitch, right? What about the one on the right?
Zero origin.
How'd you get that so quick?
I did that one first.
I did that one first. Okay, so that one on the right is not deforming. Or it is deforming? What's the one on the right do?
It is the place.
It is deforming, but is it rotating?
No.
No. Weird, right?
It's like on a degree, like you do this water the gradient rotates and stuff. And it's like-
Yeah, it gets faster as it goes in.
That's not rotating.
I thought you were like- I mean, in real life, of course it is. But the reality is that when you look at a sink, weirdly enough, this one sits right inside of this one. So fluid at large distances tends to move in solid body rotation. And then as you move in, it shrinks down to this. And then there actually is a singularity there where it drops out, right? And the dynamics change completely. Okay. Everyone happy? So the thing that I really like is derivatives. The thing that I hate are integrals. Integrals are from the devil. And derivatives are some. So we can do derivatives, that's fine. Things like curls, gradients, fucking easy. You just take the derivative. And we can look up derivatives whenever we want to. Right? Okay. Except for derivative is integral. Those are horrible. We're not going to do the math in the Reynolds transport theorem. A couple of weeks ago, I was like, or a couple of days ago, I was like, the first statement at the very first line of this paragraph is absolutely insane. It's just like math. Want to hear it? Did you read it? Yeah. I think I read it out loud for everyone. I'm not going to do it again.
Interrupt. ENS needs to get up to the observatory.
Yeah.
I can't find it.
That's the observatory key and that's the gate key.
Got
Thank you.
Thank you.
Okay. So the only thing that matters is equations 330 and 335. Where did I put them? Yeah. 335. Because we're going to use these for the things that really matter in this class. We are headed towards the fun part of the class. I know stress and all this other shit doesn't seem like it connects to anything that we've ever talked about. We talked for like 10 seconds about the laws of thermodynamics, and then we immediately moved away. Like, this class is so stupid. But instead, there is a master plan. I haven't revealed my master plan like a spider weaving a web. And this will be necessary when we derive the conservation laws. So we're going to start. I just told you I hate integrals, but we're going to start with an integral formalism. Okay? Because that's the easiest way to think about a fluid. And then we'll move towards derivatives. And this form here, the Reynolds transport theorem, you guys want to see it? It's beautiful. It's curious. There needs to be more erasers. The distribution of erasers in this class. Okay. So you start with something like this.
Start with one.
Yeah.
Do we be taking notes on this in particular?
No.
Thank God.
I mean, you can take notes on the conceptual part, but the integral is right there. It's equation 330.
Okay.
You can even read it if you want and understand what I'm about to say. Okay. Okay, so take some quantity in the fluid that you give a shit about. F. Okay, fluid quantity. And we're going to evaluate it at a location X that varies in time from positions A to B. Lost anyone yet? Okay. So there you see A and B. Those are integral bounds. And what this is essentially saying is that the rate of change here, this is dA, this is B, This is the difference in the shapes. And here's your slope. Right? You're doing the integral, which is the area under this curve. And it's just, we're just accounting like we did in computational. Just taking the difference between these regions, figuring out how much space there is. Okay? So this first one says the integral from a to b of df dx dt. It's just right over there. Okay. And what this is relating on the left-hand side is how a changing function, right, is distributing that material with time over a small distance. Okay. The only reason it's applicable to this class is that you can use it to write this. And what this is essentially saying is that we can talk about the rate of change of an object over some material property. So let's say we take a lima bean from fluid, and we want to look at how a material property inside of there is changing. Okay. So on the left-hand side, the rate of change of the integral of that property is equal to the rate of change of that property inside the fluid plus the flux of that property through the fluid surface. So here A is the surface that bounds the lima bean. So let's say it's heat. Okay. Let's say this part is heat. And the only way heat is escaping is through the exterior of the lima bean. Okay. Then this rate of change interior to the lima bean is just moving from the middle out towards the edge, right? 0. So the total rate of change inside the lima bean is 0. It's just outside. And so you just have the normal flux, right? Now maybe you redistribute it. That doesn't matter to the lima bean. Lima bean has the same amount of heat, right? If I integrate over the entire volume of the lima bean, I get 2 heats, right? Unless I lose it through the surface of the lima bean. Is that clear? So it looks like a lot of stupid math, and it is, but conceptually it's not so stupid, right? Question? That make sense? Okay. So we're going to use these ideas because we are going to derive conservation laws from first principles. Fuck. That'll suck, right? First principles always sucks. So there's our lima bean. Yay! Big. Don't look at the rest of the lima bean. It's actually for a different example, but I like the picture of the lima bean because it looks funny. I guess you could call it whatever bean you like. Pinelli. So the as we mentioned earlier, the equations for fluid dynamics can be written in 2 different ways because integrals and derivatives are equivalent, right? The way that we understand these phenomena is that one represents the area under a curve, the other represents the shape of the curve itself, the curvature. And we're going to start conceptually with the integral forms. Because if I imagine on the right-hand side that there is some fluid inside of my lima bean, then I can just let it be, right? Like I can think of water in there. But then getting towards the idea of a differential, a rate of change of velocity like this, maybe that's a little tricky to think of at first. But when it comes to computing, which we're going to do, so everyone in my computational class, remember those things. We'll do that right after this. So my goal is grand plan. We're gonna drive the conservation laws. We're gonna keep track of how many independent variables we have and how many equations we're gonna need. And then we are going to use a computer to solve those derivatives. Okay, I think in other classes, they would make you solve all sorts of like trivial examples. We'll probably do that too, just for like the basic ones, like Newton's law and shit like that. But it's more fun to try and boil water, because boiling water is hard. On a computer, not in real life. Right? Okay. So I'll show you some changes that I made to the content schedule, but they will reflect that. We'll kind of go back and forth between chapters 4. We'll finish 4. We'll do a little bit of 6. We'll do 5. We'll do 6. Go back and forth like that. Okay. Yeah. Question before we start? Okay. So our differential forms, they're going to provide coupled nonlinear equations. And this is why fluids are so fucking hard. Fluids are hard because they are nonlinear, right? They have multiple products of the velocity, for example. They're all over the place. That thing right there, that sucks. Multiply that by a velocity, that's going to suck more. So the differential equations usually don't have nice, elegant solutions, except in like pretty nice times, right? So for the most part, this is what we think of when we think of like, oh, the complexity of, drinking water, right? So how do you go from something that is smooth to something that's like changing as you pour it, right? If I pour it really quickly, it goes like this. If I pour it really smoothly, it goes like that. Have you ever seen a ball when you throw it really quick, suddenly change shape dramatically? No. Balls don't do that. They don't care. Right? Okay. Everyone excited? Medium excited? Okay. All right. Can mass be created or destroyed? No? Raise your hand for no. Raise your hand for yes. Okay. How can mass be created or destroyed?
Like exchanging a equivalent amount of energy.
By exchanging an equivalent amount of energy?
Yeah, there's after fission, like.
Oh, okay. You want to do fission? Not in this class. We can't do it in this class. It's already hard enough. Is there another way to do it? No, not in this class. Any other ways?
No.
No, not in this class. In a graduate class, you could do it. Not here. Anything else? Are there any ways to create mass? No. Let's make it easy, okay? God damn. Okay. So how would you say something like, shit, I need a good part of the board. Anything. Okay, this one sucks. Sorry. This is in your appendix. Just read it there. What does it mean to conserve mass in English, not in math? What? Keep the mass you started with the entire time. Okay, so that's, I like that as an idea that the total amount of mass doesn't change, but that doesn't really work for us in a fluid because you won't, like, let's take a parcel, right? Take our lima bean. How do I say that in words? Okay, I have a lima bean. That's my imaginary lima bean of fluid. In English, how do I describe the statement that mass can neither be created nor destroyed? Now, I know that I just said that in English, but you see that there's a little bit of nuance here, right? Yeah. Okay, so the same amount of lima bean is going to be there. Okay, what if I took a real lima bean and I squished it? What would happen?
It changes the shape, but it's still the same mass.
Would it be? A squeeze a lima bean? Everyone ever squeezed a bean before?
Yeah.
What happens? Is it cooked? It's cooked, yeah. Okay, it's cooked. Sorry. Very important. These are cooked lima beans. Okay. It squishes out the interior. Okay. Okay, so I have an exterior shell to my lima bean, and I can squeeze it And then I squeeze really hard and there's no more inside. Okay. Or maybe I can reverse that process and I can squish it back into my lima bean and it's full again. Does that make sense? What the fuck are you talking about, Mateo? Are you seeing what I'm getting at? We are not creating mass when we do these. So when we think about it in the context of a state variable, right? Something like the mass in the object. And I want to know how that's changing in the object. Well, that's how the interior is being rearranged. And any flux through the surface. Now here, this part, I can't create new mass. It's the flux through the surface, right? Conceptually. It makes sense or no? Okay. So in fact, we can write the continuity equation. Let's see if I can write that down. So this is the first thing to write. Okay. Rate of change of the density over the volume must be what?
Proportional to the change in the volume if that's concerned.
Say that again?
Proportional to the change in the volume if that's concerned.
Yeah, so assume that we're taking just a finite volume at 1
So
second.
I can change the shape but not volume.
So you could change the shape, right? But you wouldn't change the volume.
That'd be zero.
What's that?
That'd be zero then.
Correct. That's a statement of the conservation of mass. You see how that's true? Density, volume, EMDT equals 0. Right? That's what's hidden in there. Volume times density, mass, G, mass, dt. Okay. Okay, that's okay. Medium in the back is fine. Let's write it a different way. I hate that. That's stupid and I don't like it and I can't use it. Okay, so I'm gonna write what we call the continuity equation. Okay. And I did that with magic. What magic did I do it with? No, not the book. It's I read from the book. What? What magic did I do it with? Nope. I went from the top to the bottom. Wonder what it was. Oh, is it the Reynolds transport theorem? Yeah, that's right. Okay. So the right-hand side here, this is the Reynolds transport theorem. That's the top line, but it equals 0. So I still have an equality, right? They can both equal each other and still equal 0. And you do some mathematical mumbo jumbo and you have something that's much more explainable. Why is it explainable? Because the left-hand side makes sense and the right-hand side makes less sense, but I'll explain it to you. Okay. So what's this side mean? Raise your hand. In English, yeah. Perfect. Easy. How do you physically interpret that?
If something gets, I guess, in an excited state, or maybe it slows down, like a gas, like a fart.
You kind of lost me there.
Yeah.
Let's say it actually what it means.
Okay.
What does the first term mean physically? Okay, that's what Desiree said. How do we interpret that?
Is that a mass in an area changing?
Amount of mass in an area changed with time.
Yes.
Good.
So,
Either went up or down. But in mass, in a volume, a control lima bean, whatever you want to call it, change with time. Okay, what about this one? That's super easy, right? Easy, got it.
yeah, I'm trying to think that one.
Use the flow velocity, right?
Yeah, that's the flow velocity right here.
So the gradient of the density times the flow velocity also equals zero, whatever that means.
Combination of equals, yeah.
The combination of the two equals zero. I'm asking what the right term means intuitively.
We already knew
Say that again?
it. That's just kind of doing the rate of change of density. After the zero.
Well, the rate of change of density is certainly not zero.
Oh, okay.
This is the interpretation of this equation, right? This one here says at the top, the rate of change of the density over the entire volume, right? Which I can break into something usable. On the left-hand side, I have something usable, which is the rate of change of a material property like density at a specific location. And that interacts with this thing, which I have yet to interpret. How does density change in my lima bean? It's a physical mechanism by which the density changes in my imaginary lima bean full of fluid. Okay, squish it. Sure, that's like the force. But what happened to the fluid?
You got compressed.
It expelled.
Let's do the second.
Okay, I hear a lot of the right answers here. It moved through the surface, either in or out. Right? There is a flux, right? And it's driven by the flow. So in fact, when we see stuff like this, anytime you see rho u, okay, especially if you have this thing here, we call these things flux divergences. Okay? So if there's no flow in the fluid, then you can't change the density. Right? Reasonable? Yes or no? Yeah.
What was rho times u again? You just repeat it.
Well, this whole right term is the flux divergence.
Oh, okay.
This would be an incompressible fluid. Right?
This is for all fluids. What this is saying is,
If you're compressing it,
what's that?
if you're compressing it, it's basically flowing inward.
Yeah. Yeah, more particles are heading into one location. Right? So you can have different locations in it. You compress it over here. Maybe that sends waves inward. You compress the fluid in the middle. Whatever you want. Right? Okay. And we call these things fluid transport terms, flux divergence terms. So anytime that you think about a fluid property like density, you are bringing it with the fluid. Why? Because the fluid is just individual particles, right? Whether that's temperature, whether that's internal energy, whether that's entropy, whether that's salinity, all of these objects are coming with the fluid. Okay. We can write this with the total derivative, which is I think the one that I like more. But in general, There's not enough erasers.
So I might have missed it. What was the right hand in like plain English? Does it exist in plain English?
This is how, so the rate of change in a fluid.
Yeah.
Of the density.
Yeah.
Is equal to, and you can move this to the other side to see it. How much flow is moving there in space? So what changes in time is due to what leaves in space. Make sense?
If you move to the other side, it'd be negative and moving out.
Yes, exactly right. Okay. Sorry. About that one. We need it anyway. It's a lot later, but here. So you can also write it like this. Um, what's that big DDT mean there? Total derivative, and the total derivative was what, two things? The total derivative, big D over big DT, means what, and why is it there?
Is it, describes the emotional and temporal changes to the fluid?
Right. So there is an unsteady part, that's the DDT part, and there's an advection part, right? And that's the del dot part, right? So we can write it like that as well. So when the density is constant, the total derivative is 0. Okay, that makes total sense, right? When the density is constant, the total derivative of 0. What did del dot u equals 0 mean? No flux divergence, which means it's not that there's no flow. Flow in equals flow out, which is an incompressible fluid. So I just made a really weird statement. I said that for a constant density flow, constant throughout the flow field, you get incompressibility as a statement. Okay. Okay, whereas in an incompressible flow, the density of fluid particles doesn't change, but the different fluid particles may have different densities. You may need to read that again. I'll say it again. The density of fluid particles doesn't change, but different fluid particles may have different densities.
So we're talking about like so the first part is like overall, like the fluid particles densities won't change, but if you go individually to each particle, then that's when like they're different.
Right.
Densities, or?
Or you can think of it differently. I mean, you can imagine that you'd have like a fluid parcel, right? Different fluid parcels aren't going to change their densities, but him and his nearby neighbor are going to have different densities for whatever reasons.
Wait, so for this definition, particles are just parcels?
Yeah, you can think of them as parcels and particles can be put together.
Oh, okay, good.
Yeah, anytime that I draw like a square on the board, I talk about, Amazon package, think parcel or particle. Okay. And yeah,
What was the big DT mean again?
that's the total derivative. What does that mean again?
All the motional and temporal changes to that. fluid.
Yeah, so this part up here would say, breaks down into something that has a unsteady term. and an advective term. The unsteady part would say, how is it just rate of change? And then advective is saying, how is it transported by the fluid itself? You might like this version better. Doesn't matter to me. Just that the flow is inside of this gradient. That can be annoying. So you might like it outside of the gradient. Okay. 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 So a fluid is generally considered incompressible if the density does not change with pressure. What are some ways that a fluid can change its density without changing its pressure? Yeah, temperature is great. So is fluid like water a good example of that? Yes. Is it, yeah, mostly incompressible? In fact, a lot of people say, well, water is incompressible. The density of water doesn't greatly change with pressure. Go down, it's still about 1 cc per cubic meter, or sorry, 1 gram per cubic centimeter. And, but what happens when you start to boil water? Density decreases. Right? Doesn't move yet. No.
Decreases up into the point in a sense.
What?
It decreases up into the point in a sense. Boy.
So you have a cup like this. Okay, you put water in it, and it's cold. All the atoms are in there, but they're at their normal distance. So you heat them up. Now they're punching each other, and the amount of area or the amount of volume they take up increases. And the total density goes down. Same number of molecules.
Is that how you can start to describe these changes?
What?
These changes of the water, so then like it starts to evaporate after getting some.
Yeah, we probably won't do that, but you could do that. Yeah. So that'll be a boundary condition. When we talk about boundary conditions, that's this whole different thing. It's just first you want relativity and fission. We're not going to do any of those things. I mean, you can. You'll have the tools to do it, but I don't want to do them. Okay. What else did I want to say? We're making really good progress. We're gonna slam through 4. So you can take the steady form. Oh wait, hold on. I forgot one thing. Was I gonna talk about this already? Do I have it here? Oh no, that's fine. So take the steady form of this equation right here. Okay. I don't even have to do anything. And steady means what?
Does not change in time.
Does not change the time, so I can get rid of
So left side.
left side. The left side gets rid of. And I just have this funny thing. And this funny thing. Ugh. Oh gosh. What does that mean?
Really good.
Yeah. Well, the density is certainly going to be constant with time, but it's going to vary a lot with space, right?
So the gradient of the flow velocity is 0, so the faster it flows, the less dense it is.
There's a different way to interpret that. So what we're talking about here is there's 2 relationships, U and density, right? One can go up while the other goes down. One's a vector quantity, the other is not, right? So the thing that I'm looking for here is the fact that this is the gradient of this thing equaling 0. And this tells us something really important about the flow, a tool we can use to describe the flow itself.
Is it flow in equals flow out?
Yeah, I mean, flow in will have to equal flow out in a certain way, but all I'm really looking for is the fact that now we can describe this with stream functions. Because the fact that I know that the gradient equals 0 means that this thing has to be defined by something like this, right? Is that true or not?
That has to be if the gradient is 0.
Has to be if the gradient is 0. Del cross a vector function. Oh, I should have made this a vector. Okay, so I can define the fluid flow and the density everywhere in steady conditions. Okay. Questions? Psi is a thing I just made up. It's a stream function. I just created it. So I also created it over here because I said that I had omega. And I could do something like del cross u. And if I did del cross u equals 0, then I could make another thing, right? So it's a good thing I wrote these just perfectly next to one another. So in situations where the vorticity equals 0 equals del cross u, what else did we know? Based on what I'm talking about here.
Gradient of a scale.
What's that?
It's the gradient of a scale.
It's the gradient of a scalar. So I could do something like u must be del dot phi. Oh, I should stop using the 0 like that. Anyone see that? Raise the chalkboard up. So we're just using some fun properties of gradients. Okay. On the left-hand side, I have what we talked about when we talked about vorticity. You could have something like the flow pattern being totally defined by a scalar potential in a irrotational flow. Where on the right-hand side, we're talking about in a steady flow that you can define it with a stream function. Pretty cool, right? Totally useless right now. You don't need it. I'm just telling you how math goes. Okay. So now the harder one. Conservation of momentum. How would we think about that? What do we want to put into consideration when we want momentum to our line equal? Yeah. Okay, so I want to know, we did this whole thing about like, what does it mean to conserve mass? What does it mean to conserve momentum? Yeah, imagine a lima bean. I have a lima bean of fluid. So mass was easy because I can squish a lima bean and that's pretty intuitive. Lima bean comes out. Momentum is not so easy. How do I think about momentum? How do I conserve it in my lima bean?
Is this about like when like a pipe gets smaller and the fluid has to speed up?
Well, we haven't said that yet, but that's an interesting thought. Pipe gets smaller, the volume got smaller. So you think, okay, well, the fluid would get forced out. So maybe if I squeeze down the volume, right, the lima bean comes out, or the lima bean material comes out. Yeah. Is that a question? No. Do you have a question?
I was just gonna say if the line of being is moving, then the momentum is conserved. It's like a mass that has like no speed.
Okay.
Yeah. Momentum is mass times velocity, right?
Yeah, so momentum is mass times velocity.
So if mass is conserved, the velocity is also conserved.
That is not guaranteed.
Constant.
The mass can be conserved. We will separately conserve the product of the mass and the velocity. We noted here that in specific circumstances, we could get them to trade with one another, right? But we want to know what happens to their product with time in unsteady conditions. We need a generalized form that talks about the equations of motion when you think about the context of what can happen to a fluid. How can fluid in our lima beam change?
Would can't be, right? You can't-
Okay, so the lima beam can change shape. Okay, and that happens from the flow. Good, I'm gonna remember that.
We're expecting like the volume,
What's that?
but if we're expecting like the volume of it. Then it's associated with the density, so. Sorry, I've been on something big and,
Okay, let it boil for a few more seconds.
yeah.
It's al dente, you're almost ready.
Let it boil for.
What's that? Al dente is not ready.
Yeah, it is.
Whoa.
Arizona,
Okay, listen, you're talking to an Italian person, gonna tell me al dente is ready? Cancel. No, it doesn't. It means undercooked by definition. Look it up right now. I was told that's what it means. Okay, sorry.
The box always says, cook to this time, make it al dente, and then keep it in longer depending on.
Keep it longer. But
Well, usually what you do is you apply some sort of sauce and you keep it at a heat, it breaks down more in the area with flavors. But you know, with top ramen, it doesn't matter. Good. Okay, we're gonna write something up here. And I'm gonna put this on from up high, right? Have you seen this before? No. Doesn't look like anything you've ever seen before, right?
I thought it was like stuff over there.
Oh, interesting. That's exactly what stuff like. Okay. And I'm gonna give you two more pieces here. So I'm gonna give you this piece here. Rho. And this thing called G. Plus this thing. F. I'm not gonna write the bottom part. I'm fine with that. Okay. So the conservation parts that we want to think about here, on the very left-hand side, that's the rate of change of our momentum. We don't really say momentum in terms of like M, because we don't care about individual parts. We're thinking about our line. Okay, so the integrated density times the integrated volume over the line movement. And the rate of change of that will be equal to any basically body forces. What does a body force mean? Wait, yeah, so the G is the thing that's supposed to draw your eye to it. So for example, right, let's say you're in a gravity field, then this piece here will change your momentum. Right? The fall. What's this piece? Someone actually already said it. I wasn't. So this will be an external force that's occurring on shape itself. This is acting on A, which is the exterior of my yeah, pressure. I haven't said pressure yet, it's just F. Okay, we're gonna this will be unknown. We'll figure out what it is, but maybe there's pressure. So here I have something that acts on the whole body, the whole line of it. Here I have something that acts on the surface. And both of those things can speed up or slow down my fluid. Is that fair? Are there any other body forces? Nope. Air is not a body force. Air is not a force. Air is not a force as far as I know. Maybe it's air, earth, wind, fire. No. You're thinking of the buoyant force? I don't know what you're saying.
Air pressure.
I was thinking that.
Oh, okay. What were you thinking?
Just air.
It just said air. Okay, okay. Anyone have a body force?
You mentioned. Yeah.
Ah. So what if I suspend my liquid in a magnetic field or an electric field? That'll work on the whole fluid, right? You want to do that in this class?
No.
No. Okay. Are there any other examples of body forces? Not that matter to you. We'll mostly only do gravity. Okay. Okay. And there's that piece at the bottom. What is a conservative body force? And I'm not talking about Republicans. What do you mean it doesn't change with time? Okay.
I guess.
What does it mean for something to be a conservative force? It's path independent. And we said this when we talked about the two laws of thermodynamics, right? So it doesn't matter how you get there. When I go from point A to point B, I can get the same amount of energy out of it as when I go from point B to point A. Right? Right? Yeah. Okay. It's path independent. So as I, oh my God, should I do it? I want to your table. I don't think I can, but if I climbed onto the table, imagine that I climbed over the table really gracefully. Okay, and then I jumped down. Versus if I like crawled up and sort of like rolled and then stood up really ungracefully, right? That would be two ways of getting up, two different paths, but I have the same energy as when I jump down. Path independent. Okay. Okay. So now you have conservative body forces. So sorry, what was the right hand side again?
All the body forces and
Surface forces. Surface forces. Okay. So we have this really wonderful integral there that just is like F. Totally don't give a shit, right? And so now we're gonna have to figure out what F is. Okay. So okay, that's fine. That's fine. That's fine. No one's scared. Surface forces act on contact with the fluid. Okay, directly. Body forces act at a distance, right? Like gravity and electromagnetism. What are some example of surface forces? One was already said. Pressure. Good. All right. Anything else?
Normal force for containers.
Normal forces. Wait, say that again. Normal
Normal
forces
force
for
in like a
container.
container.
Sure. Yeah. Surface tension. Okay. Yeah, that's at the boundary. Yeah. That was the one I want. I erased it from that board. What you feel at the end of the semester?
Right.
Stresses. Remember, stresses act on the exterior of a parcel to change the shape of the particle. The parcel. Okay. So these forces have to be resolved in the direction that they act and on the face they act on. So we get tensors again. So you're wondering, why the hell do I have SO and you don't really care about it? Here's why you care. You will resolve the tensors in their directions. And you'll have in your math, when we do this in computation, you'll have a little array. You have a stress tensor array, and you'll have a rotation strain array, And you'll have all of these beautiful arrays, and you're gonna see we're gonna do some like witchcraft to combine them in really fun ways. Then we'll create words that don't mean anything in order to make them go away. It'll be really fun. Okay? Excited? You excited? Yeah, okay. So let's go to Cauchy's equation of motion. I believe that is on. Okay. We can write it like this. Because we hate integrals, right? Remember?
Yeah.
Okay. So we can just write d. That's a d. T. U. And I'm going to use index notation here because we're going to have tensors. Rho. V. And you may be asking yourself, what's that TIJ, Mateo? Sounds like the rotation thing. Okay, so there's a T in rotation. I see where you're going. I see where you're going. What is it? What?
The temperature.
No. Temperature is not a tensor. Temperature is a scalar. It's a scalar property. It's T for tensor, very close. It's the stress tensor, folks. We just said it. It's right above that. Okay, you're stressed end of the semester. Don't forget to write your stress tensors with a T. Okay, so we're going to talk about the constitutive equations necessary to solve these because we haven't really been paying any attention. But here you have one variable, so that's the density. And you have 3 variables for the direction, right? And so far I have, okay, 3 variables or 3 equations for this. And if I go over here, where's my differential equation? So I have this one here. This gives me a couple equations that I have to solve. I need more equations. And in fact, I need a way to relate the stresses to the fluid itself. Okay. Is it clear why I would need that? So T is going to be differentials of the fluid flow. So it's going to be, you know, pieces of flow moving into places where other pieces of flow are. So it'll be differentials of their flow like this. Okay. That'll only have functions that have things like u's in them and x's in them. Right. So far we have a bunch of equations for u. We have some equations for rho. We may or may not have an equation of state, something that, for example, relates the density to the pressure and the temperature. Once we have this one here and this one here, if the pressure only depends on the density and it doesn't depend on the temperature, then you're done. But usually you have a T, right? And so you have one more variable, then you have total number of equations. Does that make sense? So we'll talk about what are called constitutive equations. And this is the relationship between stress and deformation. Thankfully, T will be symmetric and all the shit that we did before will actually matter. And then we're going to move it. We're going to make it really nice. We're going to throw it all together and we'll put it back in the pot. That is our continuity equation. And we'll get the Navier-Stokes equation. Okay. Now, once we have the Navier-Stokes equation, we'll talk about boundary conditions. We'll talk about some self-similar solutions, like places where fluids look exactly the same at very different scale lengths. And then we will put them into a computer and you will brush off your computational skills. And we'll do differentials because we have differentials here and a computer can simulate them. And we will boil water. And then we'll go back and we'll do streamlines and vortices because that's very powerful and fun stuff. And then we'll go back to computation and we'll do that same formalism on the computer. And then we'll go on to all of our fun examples. Okay. Yeah.
What's the time frame for us to actually start coding?
Well, let's see. I did. How many slides did I do today? I did 13. So on Monday I did 9, which is the least number of slides I've ever done in a class in an hour and 15 minutes. So we get about 1 slide per 10 minutes. And so this is where I'm headed. Okay. So non-inertial reference frames, we'll just touch on that really briefly. Special forms of the equations, Bernoulli's equation, Boussinesq's equation, boundary conditions, and all of these have multiple topics in them. But then you get to fluid dynamics. So these are the topics, and I'll leave this as it is right now, unfinished, so you can see what topics we'll actually cover. But, you know, you tell me 2 weeks, maybe 3 weeks. So if you don't remember how to code or you never learned how to code, talk to me. Finally, you have a homework, I believe. Oh my God. Okay, so that's this. And then just to be clear, you only have to do one of the 2 of the bottom 3. I just like both the problems. They're both fun. You can do both of them. I won't, there's no bonus, no harm. And I have your homeworks. So bring me 1.2 and I'll trade you these. Questions, comments, concerns? Oh, sorry, 1.20, if you didn't have it already. Yeah. That's exactly what I've done. And then don't forget that next week we'll talk about doing your initial check-in. Yeah.
Thank you.
And if you have any questions, feel free to have me.
No. Lost, dude. You're hella lost.
Great success.
We
We can do appointments, yeah.
So just a.
Yeah.
Okay.
You too.